Thomas, I don't know,
Yes.
you might have other things. I know you sent me an email with a list of things you're going to do, but I've got another question, and now I'm just throwing this at you without you being able to prepare. Although it was a question I think that I mentioned in the car on the way back from Scotland, which was so like a bicycle wheel. We're back to bicycles again. So a bicycle wheel, if you think about the outside of the wheel, a little creature, let's say an ant or something, on the outside of the wheel, if you just spin it, it feels like it's going round at a certain velocity. If you put it further inside the wheel, so it's closer to the centre of the wheel,
sliding down the spokes.
Sliding down the spokes, let's say, yeah. So let's say halfway, it will feel like it's going slower because it's closer to the centre. So
the inverse. It'll feel like it's going faster.
It'll feel like it's going faster, will it?
Yeah.
Okay. So what happens? My real question is, what happens at the very dead centre of the wheel?
Okay.
So you've said it's going slower on the outside. It feels like it's going slower on the outside as it gets closer and closer. Oh, this relates to your thing about gyroscopes, I suppose, isn't it?
So gyroscopes kind of like the pinnacle of this kind of the basic classical mechanics. Gyroscopes, in my opinion, is like it requires a lot of things. You need to know kind of all the basics then before you can get gyroscopes. And this sits in the middle. So this comes under what's called circular motion, which is probably fairly straightforward, I guess. Yeah, circular motion. So it's a quite simple answer actually. What happens when you get to the
give us that
rotation? So that one you'll just rotate very quickly. So
there is not a point in the middle of the wheel that's not moving at all.
Well, it depends how the wheel is fixed to the axle. If it's on a bearing, then sure. But assuming whatever's spinning, you've got like a spinning top. That is just rotating very quickly. Okay. So you'll sit down and then you'll just spin around with it. Your legs will be flying around. You'll just rotate about that axis.
So the very, very centre, you're still rotating.
Yes, you're just rotating about really the axis. You're rotating around the sort of axis of symmetry. Okay. So that's unless, like I say, if you're on a bearing, if whatever is fixed, this is a simple case.
Okay, that's interesting. So somebody told me the opposite years ago, and I've always believed that the centre of the circle, it's essentially not moving at all. So I was wrong all these years.
Yeah,
so that's actually, and I've learned something new.
That's interesting because there's some nuance and some subtlety there, but essentially as a person that exists in reality, you'll spin around it. So this kind of actually leads on to my second thing, which was talking about spinning of a body, which is why does, in your analogy, the ant move faster when he's halfway down the spokes and he's on the side? So there's a couple of things here. There's essentially the boring answer, which is conservation of angular momentum, fine, which is just basically in the same way you've got linear momentum, which is your mass times velocity, basically how much energy you're carrying as you're traveling through space. If you're spinning, there's an equivalent for spinning as your spinning momentum, and that has to be conserved, so you have to move faster. Now, that's a boring answer. That's basically just energy is conserved, therefore true. But I guess a more intuitive way, at least for me, to think about it, and this kind of goes back to, again, when I was first learning this stuff, the definition of velocity is the change in displacement with respect to time. So basically, how quickly you displace a thing. All right. So if I move something from A to B, how quickly do I move it from A to B? That ratio, the distance divided by the time taken, that's your velocity, your speed. Right? So a little bit of a caveat there. speed is just how quickly you're moving. Velocity is how quickly and in what direction. So there's a bit of a caveat, and that will be important when we talk about gyroscopes. But anyway, just for now, your speed or velocity is defined by your displacement divided by your time. So your change in position divided by change in time, how long it took you to get there. And everyone is learning this. I'd always say change in position or distance divided by time. And my teacher was always really anal about this, displacement. And I was always like, okay, like who cares? Displacement, fine. You're using some more jargon. It doesn't matter. It means the same thing. And it kind of does mean the same thing. But when I say distance over time, I kind of think in linear distance, right? I'm talking like, if I, on a racetrack, I have like a 100-meter sprint. Okay, you got the start of the thing and then a straight line to the end. That's distance. Distance, of course, doesn't have to be in a straight line, right? If you're moving in a circle, that distance will be travelled on an arc of a circle, right, along the surface. So you've got regular velocity, which is just your distance over time, but you've also got the sort of more formal definition, displacement over time. So if you're moving in a circle, the distance you're traveling is essentially the angle subtended, right? So as the clock, moves around, the distance between the hands, you could describe that by, okay, well, they've moved, once they're like this, they've moved that distance away. Once they're down here, they've moved that distance away. Or you could say, well, they've moved so many degrees, right? So by the time, you've got 3 o'clock, well, that's 90 degrees. Okay, so you could measure the distance between the two clocks and say, well, that's, a few inches. Or you could say, oh, they've just rotated 90 degrees. The second hand is displaced 90 degrees from the first hand. And then you can measure how long that will take. And then you have your angular velocity. So essentially how quickly you're traveling through angle.
90 degrees. But on that arc, so it's not going in a straight line, it's going on that arc, that 90 degrees,
Yeah. So in terms of just kind of relating the two, the arc of a circle is equal to the radius multiplied by the angle subtended.
Okay.
So it's just a definition of how to get that distance, how to get that length.
So that would be equivalent to straightening that arc out. Essentially, that's what you get.
Yeah. If I multiply the angle I've just travelled through by the radius of the circle, and then I straighten it out, that's the same.
Yeah.
Okay. So that's your angular velocity. So we're now thinking in a different coordinate system to your kind of usual Cartesian coordinate system. So that's your x, y, z. That's your kind of standard forward, backwards, left, right, up, down. X, y, and z. This is now a polar coordinate system. So what we care about is your radius from some origin. So how linearly far you are from that origin, and the angle you've travelled relative to that. I guess, to a line bisecting that origin. So we're now in a polar coordinate system. Polar, you can kind of think, okay, polar angles, okay, fine. But yeah. So if you think about this, right, if I have some angular velocity, what does that mean? Okay, I've just said it's, well, how many degrees do I travel through in a certain time? Now, if I have a large radius, then the arc of that circle is going to be small, right? Because, if I travel 5 degrees per second, 5 degrees, that length is going to be different. How do I say this?
So let me offer a metaphor. So the difference between a 10-pence piece and a plate, let's say a dinner plate. So 5 degrees on a 5-pence piece versus 5 degrees on a dinner plate.
Yeah, so the degrees is going to appear the same. But if we take the plate first, 5 degrees, okay, if you draw that out and then basically draw the arc, it's going to be quite large, radius times that. So if that's your angular velocity, if I now decrease my radius, the angle's going to have to decrease to keep the same speed, right? If I'm traveling at the same speed, I'm displacing myself by the same amount in a given time, right? So if I take that that 5-degree wedge out of the plate, measure how long that is, and then I wrap it around a 10-pence piece, that distance is much more the larger. Sorry, it's going to travel through more angle in the smaller radius than it is in the bigger radius. So essentially, in terms of conservation of distance traveled, that wraps around more times the smaller piece than it does the plate. It's kind of how bike gears work, right? If you're in a bigger gear, the one connected to your pedals is bigger, and then the one connected to your wheels is smaller, because you want to, in a small angle, travel, small angle, that distance correlates to quite a large change on the smaller gear. Therefore, that wheel spins almost a full revolution for a small angle. That's essentially what's going on. You kind of, you're displacing by some amount. And if that amount is fixed, if I decrease my radius, then that wraps around the smaller circle. So does that make sense?
I think so. Yeah, I think so.
So you're essentially traveling more distance per time if your radius is smaller.
Right. Okay. Yeah.
So, which is what, so that's another way of saying it is, conservation of angular momentum.
Okay.
With angular momentum, you've got momentum linearly is your velocity times your mass. If you're spinning, your mass, you use what's called a moment of inertia, which is essentially your rotational mass. It's your mass multiplied by the distance away from the rotational origin, and your angular velocity. So your angular momentum is just a product of those two things. So as I mentioned before, the distance along the circle traveled on the larger radius corresponds to more angles attended on the smaller circle. Yeah, so that's basically why. Cool. So that answers that question about the narrower your orbit, the faster you spin.
Yeah,
makes sense now. Okay.
Yeah. Okay.
Cool. So the next step then is to extend this to gyroscopes, which.
Okay. So let's just explain what we're talking about with a gyroscope, because not everybody might know what that is. So what is a gyroscope, first of all?
So this is basically a spinning wheel on a stick that kind of steadies itself. Like if I spin a gyroscope, so imagine a disc with a pole through it. If I spin that and then I put the stick, the pole through the spinning disc, if I put that on a little stand, it won't topple over. It'll process around, it'll spin around, but it won't topple. It won't fall over until the wheel has stopped spinning. If you or another experiment that people do to kind of show this sort of thing is they'll connect, they'll attach a bike wheel on its sort of spinning axis to a string. They'll spin the wheel really fast, put it upright, and then let it go. And now you'd think, oh, the wheel's just going to fall down, but it doesn't. It just stays still until it stops spinning, and then it goes limp. It's partly also why bikes stay upright. It's difficult to just, if you're cycling, to pull your wheels like that, it's kind of hard to do. When you turn, you kind of tilt, right? And also, why do bikes stay upright? It's the same principle.
The other one that's perhaps worth thinking about as a kind of illustration that I know a lot of people use is the ice skaters. When they're doing the sort of spins, when the ice skater sort of gets small, and the smaller they get, or the closer they bring their arms in, the faster they go, and then they move their arms out. And you can also think about if you've got two people there, so like the ice dancing, when they have a partner that they're spinning around, that's kind of acting like a gyroscope, isn't it, at the same time?
That's closer to sort of regular circular motions. That's kind of what I was talking about with conservation of angular momentum. The smaller they get, the closer they are to that central axis, so the faster they spin. So so that's your person getting to the center of the circle that's spinning.
Right. Okay. Yes, that's right. That's right. Yeah. Okay. Cool.
So a gyroscope. Why doesn't it fall down? If I spin the disc really fast and put it on, why does it process and not fall down? You would think it has some weight, so you'd think, and the disc also is like normally halfway along the stick. It's not at the bottom. So you've got a heavy bit, this pen here, I've got a heavy bit in the middle.
If you're on YouTube, you can see this. Obviously, if you're listening on on a podcast, you can't. But Thomas is explaining it to us using video. So head over to our YouTube channel.
Yeah. Okay. So I have my pen.
Okay.
And I tilt it at some angle. And imagine halfway along the pen, I have a disc that's spinning really quickly. Now, if I just let this go, you would imagine it's going to fall down. But what actually happens with the gyroscope, if that's spinning, is it doesn't fall down. It just rotates about that axis. And it only falls down when the disc stops spinning, which feels strange, right? It doesn't. It feels like that kind of breaks some law of physics. Why? There's nothing keeping it up. Surely spinning shouldn't have anything to do with counteracting gravity. So this isn't particularly intuitive, and it took me a while to kind of understand why this even matters, right? Like I learned the maths when I
should say before we explain it, I should say to our listeners that I know this is really, really important in lots of things that we use and take for granted, such as mobile phones or smartphones. That the screen can recognize whether it's which way you're holding it, and it will flip the screen accordingly. This is all apparently due to some very, very tiny gyroscopes in these devices that use these sorts of properties. So it's something that we use all the time. I'm sure you know other uses for this, but it's kind of a really, really practical bit of knowledge that is used in everything.
Aviation as well, like aeroplanes use it, and that kind of stuff. Like it's a useful thing, but it feels just like a fun desk toy instead of something useful. Like a magic trick that people don't really know how it works. I mean, I know when I was a kid, a few people would tell me, "Oh, people don't even know where bikes stay up." Which, thinking about it now, maybe they didn't know. But it's a good question, right? Why doesn't a bike fall over unless it's stationary, right? And it's because of this disc So, if you take my example of the pen on some angle with the disc halfway spinning, so what if I let it go naively? You would think it's just going to fall down because the spinning shouldn't matter, but its weight is pointing downwards, right? So there's two types of forces at play here. There's your regular linear forces, I'm going to call them. So that's weight pulling down. You've got the reaction force on the pivot. So I've got my pen rested on like a little wedge thing on like a little stand. So there's the force of the stand pushing up on my gyroscope, and then I've got the force of the weight pulling down. All right. So those are your linear forces. You also have your angular forces or your torque. So this is what torque is. Torque, T-O-R-Q-U-E, torque. This is a rotational force. So it's now, instead of mass times acceleration, it's moment of inertia multiplied by angular acceleration. So it's just the rotational equivalent to a force. That's torque. So let's resolve these guys. Let's see why isn't it falling down? So the only force is acting in whether the gyroscope topples or falls down rather is its weight pulling it down, but that's counted by its by the stand pushing upwards. So those guys are in perfect balance. Linearly, the forces are equivalent, so there's no problem. The stand isn't collapsing under the weight of the gyroscope, so the weight must equal the force reaction from the stand. So there's no linear force actually pulling it down. Sorry. The force pulling it down is being countered by an upwards force. So in your vertical axis, where you would fall down, it's in equilibrium, it's zero force, which feels weird, but linearly that's all the forces working. Now rotationally, what rotational forces are at play? So now this is kind of interesting. So when you have rotational bodies, and this is a product of algebra rather than physics, if I have two arrows or two directions, two vectors, which are quantities in a direction, if I rotate one to the other one, by convention, the resultant vector is perpendicular to that. So I'll kind of explain a little bit what I mean. So if I have like a bolt and I'm trying to twist it with my little wrench, I'm pulling it downwards, or pushing it downwards, so I have a force downwards.
Yep.
So that's one force. And well, if I manage to get it, it will rotate. My wrench will rotate.
Yeah.
So I have a force that's now rotating, which means, mathematically speaking, the resultant vector is out of the page, is coming towards me. If I'm wrenching it downwards, it's coming towards me. That's the force by convention. That's the direction of the force. So with torque, the rotational force is perpendicular to the direction of the driver. Does that make sense?
So when you say perpendicular, so again, use this illustration of the spanner, I suppose, undoing or tightening a nut.
Yeah.
We know that this might be red herring, so we can chop it out if it is. But the longer the shaft, the easier it is to tighten or undo it. So as I'm tightening it, where is the force? And you're saying it's perpendicular.
So what does that mean? Yeah. So as you're tightening it, you're applying a force to it. So that force is traveling presumably downwards as you're tightening.
Yeah.
Right. But the torque, the rotational force, is coming toward you. So it's perpendicular to the direction of your applied force.
Okay.
So there's a very detailed mathematical reason for why, when you have vectors in a space that are and you take what's called a vector or cross product, you get a perpendicular vector.
Okay.
But for now, basically, if you have a rotational body, the direction of the vector associated with that rotation is perpendicular to it.
That's really interesting. Okay. Again, that's not how I would have thought. That's counterintuitive. Okay, interesting.
Yeah. So when you're thinking about rotations, it does get a little bit confusing. Now, unlike linear force, which is kind of easy to imagine, if I drop a ball, its weight is pulling it down, or it's on a spring, the spring's pulling it up. Rotational forces, you have to think perpendicularly. Everything's orthogonal to each other if you're going to be more general. So I've got my gyroscope and it's on its little stand. So the weight is pulling it down, which means the torque is acting, I guess, in this direction towards you, perpendicular to the direction of the weight. So there's the torque force associated with it is pointing over here. Okay. But if I'm spinning the wheel, right, I've got my wheel in the middle of the gyroscope, that's spinning. That has now an angular momentum associated with it. And as I mentioned before, angular momentum is also a vector. And the rate of change of angular momentum is by definition torque. So that's just the same way as force equals mass times acceleration. Rate of change of angular momentum is torque. It's the same thing. It's just the rotational equivalent of Newton's second law. Cool. Okay. And that's equal to your moment of inertia, your rotational mass, if you will, and your angular velocity, how quickly you're traveling through angles. So, so you've got that coming perpendicular to the plane of rotation. So I'm rotating my disc along, I guess, the pole that's holding the disc. That is the direction of your angular momentum. Okay. So if my gyroscope falls down, the direction of that vector is changing, right? So the plane of the disc, the face of the disc is changing its direction. Now, there's another important thing when it comes to torque, and you mentioned this. The farther you are away from your pivot, the easier it is.
Yeah.
Now, an alternate definition of torque is force multiplied by perpendicular distance from the pivot. Right? So if I'm perfectly level with my nut and I push it down, it's going to be whatever force I apply multiplied by that distance. and that's how much rotational force I'm adding. So the farther I am, the larger that multiplication is, so the more rotational force I'm adding, therefore that's a lot easier, right? But it's specifically perpendicular distance, not linear distance. But supposing you're only applying force downwards, suppose you've got, instead of your hand, you attach a bucket and you put some bricks in it. As the spanner is rotating, the bucket's weight is always downwards. So the closer to the axis the bucket gets, the less, I guess, pulling force it's got, the less rotational force it's got. Does that make sense?
I'm not sure about that.
I 100% guarantee.
Okay. Okay.
Yeah.
Okay. So let's imagine that I'm trying to get a bracket off the wall, and that bracket, there's a nut that is connected to a bolt. So we're trying to get that nut off the bolt.
Yeah.
So I get a nice big spanner, and I'm doing it over there. That's no good to you. We're back to YouTube listeners again. So I've now got hold of my spanner, and I'm pulling it down to undo that nut. It's the same distance from my spanner to the nut. Doesn't matter how far I go down. It's the same distance, isn't it, from the nut to the spanner. So when you say it's perpendicular, what do you mean by that?
So, yeah, you're correct in this sense. If you're the driving force, if you're the man holding the spanner, that distance is the length of the spanner, so that doesn't make any difference. But if I attach, so imagine initially you apply 10 newtons of force, say 10 kilograms worth of force in your hand. Now, as you're pushing, you're going to change the direction you're applying that force in to match.
I first of all pull down, and as I'm going, I'm gradually pulling,
exactly
across.
So,
okay.
And imagine you're applying effectively 10 kilograms worth of force. Okay. Well, if I attach at the end of the span, if I attach a rope and a bucket, and I put 10 kilos in the bucket, right?
Yeah.
At the point where the spanner is, I guess, perpendicular to the ground, horizontal.
Yeah.
You and the bucket will apply the same force.
Right?
Yeah. The bucket can only pull that directly downwards because it's weight, whereas you can, move. The closer the horizontal spanner gets to being vertical, the less torque, so the less effect that bucket is going to have.
Okay, got you. Okay.
Does that make sense?
Got you. Yes, it does. Yeah.
Unlike you, who can move the direction of the force. The bucket is always pulling down because it's just weight.
Got you. Yeah.
So that's what when I
that's what
talk
about
this.
Right. Got you. Yeah. Got you. Okay.
Yeah. So the closer you are to the pivot, which is essentially what's happening when you're rotating it, the less pull you have. Right. Okay. So back to the gyroscope. So I've got my gyroscope resting on its stand. The wheel is spinning. So my angular momentum vector is along the central axis of rotation. So it's my stick basically. So if that falls down, the distance between the pivot and the center of mass is going to change. Right? Does that make sense? So
say that again.
So as my gyroscope falls down, if it were to fall down, the distance between the pivot and the center of mass of the gyroscope will change. In the same way as the bucket example, it will get closer to it.
Yeah.
By the definition of angular momentum, which is moment of inertia times by the definition of torque, which is distance from that pivot multiplied by the force, that's going to have to change, right? But if I have my flywheel spinning, my disc is spinning, again assuming no friction, well, then there's nothing slowing that down, right? And that's going to continuously spin in a no air resistance frictionless world, which means if my gyroscope falls down, there has to be a change in angular momentum, because now the distance from the center of mass to the pivot is decreasing, which means the moment of inertia, which is your rotational mass, has also decreased. Therefore, my angular momentum has to have decreased proportionally. But if there's nothing in the rotational system messing with the spinning, the only thing is gravity pulling down, then by the laws of conservation, the angular momentum is not allowed to change. So because the angular momentum can't change, because the spinning is happening and the moment of inertia has to be fixed, that means because the linear forces are balancing, the rotational forces also have to balance, which basically counters the falling down of the gyroscope. It's only when the wheel slows down that the angular momentum decreases, thus allowing the radius, so the distance between the pivot and the center of mass, to decrease, therefore it can fall.
So in a world without air resistance again, then it would never stop. It would just carry on forever, basically.
Yeah, exactly. Because of this relation of torque, which is distance from pivot multiplied by force or weight, and angular momentum, which is moment of inertia times angular velocity, moment of inertia here being mass multiplied by the distance from the rotational axis. So basically those things are going to have to change. One has to change if it falls down, which means the other one can't be constant. So these are perpendicular axes, and perpendicular vectors don't affect each other. They don't, if I drop this little pot downwards, or I throw it horizontally at some speed, it's going to fall at the same rate downwards. It doesn't matter how fast I throw it to the left. Downwards, the force is the same. They're perpendicular vectors. They don't care about each other. The same is true here. The spinning doesn't care about the weight pulling on the gyroscope. So the weight on the pulling on the gyroscope can't affect the spinning, but they both have to balance each other out because of the perpendicularness of vectors. So that's why gyroscopes don't fall down.
That's how gyroscopes work. All right, so we're coming to the end of our podcast now because I'm tired. My brain hurts. But just my last question then is a stupid question, a dumb question, but I'm going to ask it anyway. Okay, so I sort of mentioned then that if there's no air resistance, then that gyroscope effectively carries on forever. So if we set up a bell chamber or something, we'd suck out all the air in that chamber, then could we see that happen? Would a gyroscope continue to spin in that way? I guess surely somebody's tried that as an experiment, and it can't be true, can it? We're kind of into perpetual motion territory here, aren't we?
Yeah, so you're right. In air resistance, I was a little bit cheeky, isn't the only thing resisting the rotation. There's also, now I'm rotating about an axle, presumably, so there'll be some friction on the bearing or whatever thing is spinning is touching a surface. And even in the ideal case of you have really good bearings or something, there is still contact between two bodies. If there's contact between two bodies, there is contact friction. So there's a resistive force there. So air resistance isn't the only stick in the mud. We also have contact friction between materials.
Okay, cool. Good. All right. Okay. Well, that's fascinating. So if you're anything like me, you'll need to listen to that again, folks. And obviously, you can talk to Thomas on the Facebook page. That's the best way to communicate. So from me, that's it. I mean, I've answered my question that I had for all those years about my cycle. So thank you for that, Thomas. That was really, really interesting.
No problem.
Great stuff. Right. Okay. Cool. So next time we must do a psychology one. And we were talking about doing mind over matter, given that we are called matter over mind. This whole idea about mind over matter, can can the mind sort of defeat physics, or can it defeat, or can it break the laws of physics and so on, or science that we think we know? Lots of people think it can. I'm going to do a bit of research on that and see what I can find out. So that's next time.
Sounds good. Nice one.
Okay, good. Thank you, Thomas. Really enjoyed talking to you today, and we'll see you again next time. Bye for now.
Awesome. Bye-bye.
Bye. Bye.